Hello, so today we're going to prove this glorious identity that we usually prove using Pythagoras using trigonometry. And then you can imagine how you could use it to actually prove Pythagoras' theorem itself. And we're going to do it using this line. So, let's go. Let's start by defining some of the things about our right angle triangle. To start with, why don't we use that unit triangle that we would usually use in this proof, except we would use Pythagoras. But here what we're going to do, we're going to call this angle theta. This is a right angle, and we can call this angle alpha here. In this right angle triangle up here that we've created, we can also work out what the angles are, because in this big triangle, A, B, C, we know that if one angle is theta, one angle down here by C is 90 degrees, this angle up here has to also be alpha, because we know from triangle ACD that theta plus alpha have to be 90 because the angles inside a triangle sum to 90. So that means that the angle DCB is also theta over there. Now, once we've done that, we can start using trigonometry. Let's try and find this length here, AC. And we're going to use the triangle ABC to do that. We have that its hypotenuse is 1, and the angle down here in its bottom left is theta, and we want to find AC. So we have an adjacent and a hypotenuse. So we're going to do that cos theta, because cos theta equals the adjacent over the hypotenuse. And the adjacent is AC, the length we're trying to find, and the hypotenuse is just 1. So we actually get that cos theta straight up equals AC. You might notice this is actually very similar to how we prove this identity using Pythagoras, except we've added this extra line in the middle. So let's keep going. By the same process, BC ends up being sine theta, because we use the same triangle, except we're trying to find the length BC. So we do opposite over hypotenuse, BC over 1, which just gives me BC. So the length BC is just sine theta. Now, if you had Pythagoras here, you'd just say, well, cos squared plus sine squared equals 1. There we go. But we're not going to use that. Instead, we're going to look at this triangle ADC. So once again, we know that this whole length is 1. And in this triangle, we have that this is cos theta. AC is cos theta. Now, in the triangle ADC, we have a hypotenuse of cos theta. We have a 90 degree angle. And what we're going to do is we're going to try this length here. Now, this length, we can actually just use trigonometry again, because we have that cos of the angle theta down here is equal to the adjacent being that length A, over the hypotenuse, which we know is just cos theta. So that length AD, which is little a, is just cos squared theta. Cos squared theta. Similarly, we're going to look at triangle DBC. In DBC, we have the hypotenuse is sine theta, and we're going to try and find the adjacent length here. So we have a triangle, looks like this, where this is B and this is sine theta. This angle is theta, and that's a 90 degree angle. And we're going to use that sine theta is just the opposite over the hypotenuse, B over sine theta. So B is also sine squared of theta. Can you see how we've got to our answer? Well, we have in AB that we know it's 1, we defined it as 1, but also it's cos squared of theta plus sine squared of theta. Therefore, cos squared of theta plus sine squared of theta has to equal to 1. And there we go. What a lovely, lovely proof. Now, initially, I found this proof in a 3 blue 1 brown video, and I actually made a long time ago a blog post on my website, Hellick Maths, where I talk about it, and it's mentioned in the lecture here. I will put the links to this in the description below. And actually what I did is I created a worksheet based on this proof that students can actually use in class. You can see down here that actually what we do is we use it and use the idea of similar triangles to just prove a squared plus b squared equals c squared completely generally. And actually, when you go to this blog post, there's another bonus trigonometry proof on the right here that's fantastic to try yourself. So I'll put the links for those in the description below. Thanks for watching.